Good afternoon. My name is Christopher Guzman, and this is my presentation of quaternions for abstract algebra. So let's start with the definition. The quaternions are a member of a non-commutative division algebra first invented by William Rowan Hamilton. The idea for quaternions occurred to him while he was walking along the Royal Canal on his way to a meeting of the Irish Academy. And Hamilton was so pleased with his discovery that he scratched the fundamental formula of quaternion algebra on a bridge. And that formula is I squared equals j squared equals k squared equals I times j times k, which equals -1. In mathematics, the quaternion number system extends the complex numbers. Hamilton defined the quaternion as a quotient of two directed lines in a three-dimensional space, or equivalently as the quotient of two vectors. Quaternions are generally represented in the form of a plus bi plus cj plus dk, where a, b, c, and d are real numbers, and I, j, and k are the basic quaternions, where I squared equals j squared equals k squared equals I times j times k, which equals -1. Here are some properties. Multiplication of quaternions is associative and distributes over vector addition. Except for the scalar subset, it is not commutative. This is a multiplication table emphasizing non-commutativity by the colored squares. You can see here that j times I equals -k, and I times j equals k. Order does matter for multiplication of quaternions. So let's start with an addition example. Let's add z1 plus z2. z1 is going to equal 1 plus 2i plus 3j plus 4k. z2 is going to equal 5 plus 6i plus 7j plus 8k. So here we have z1 plus z2. We'll put like terms together, so we'll have 1 plus 5, 2i plus 6i, 3j plus 7j, and 4k plus 8k. Add that together and we're going to get 6 plus 8i plus 10j plus 12k. So let's try some multiplication. So we're going to have z1 times z2. z1 will equal 1 plus 2i plus 3j plus 4k. z2 is going to equal 5 plus 6i plus 7j plus 8k. Let's use our multiplication table to help us out. And here we'll have z1 times z2. So we'll have here 1 times all the terms on this right side. So that's 1 times 5 plus 6i plus 7j plus 8k. We'll do the same thing with 2. 2i times 5 plus 6i plus 7j plus 8k. Do the same thing with 3j. And again with 4k. So let's calculate each one of these. 1 times that whole term will just equal that whole term. And then here it gets interesting. We have 2i times 5, which is 10i. 2i times 6i is going to equal 2 times 6, which is 12. And I times I, which is -1, so that's -12. 2i times 7j is 2 times 7, which is 14. I times j, which is k, so that's 4 plus 14k. And then we have 2i times 8k 2 times 8 is 16. I times k is negative j, so that's negative 16j. 3j times 5 is 15j. 3j times 6i, 3 times 6 is 18. J times I is negative k, so that's negative 18k. 3j times 7j is 3 times 7 is 21. J times j is negative 1, so that's negative 21. And then we have 3j times 8k. 3 times 8 is 24. And j times k is I, so that's plus 24i. For our last one, we have 4k times 5, which is 20k. 4k times 6i. 4 times 6 is 24. K times I is j, so that's plus 24j. 4k times 7j. 4 times 7 is 28. K times j is negative I, so that's negative 28i. And for the last one, we have 4k times 8k. 4 times 8 is 32. K times k is negative 1, and we have negative 32. Let's collect like terms. 5 minus 12 minus 21 minus 32. Let's collect the i's and then factor out the i's. So we have 6i plus 10i plus 24i minus 28i. Let me just factor out the I here. We'll do the same thing with the j's. So we have 7 minus 16j plus 15j plus 24j. And then for k, we have 8k plus 14k minus 18k plus 20k, and factor out the k. When we calculate this, 5 minus 12 minus 21 minus 32, that's going to equal 60. Negative 60, I'm sorry. So here we have 6 plus 10 plus 24 minus 28. That's going to equal 12i. Here we have 7 minus 16 plus 15 plus 24, and that's going to give us 30j. And then here we have 8 plus 14 minus 18 plus 20, and that's going to give us 24k. So that is the solution to z1 times z2 is negative 60 plus 12i plus 30j plus 24k. Here are some extra details on quaternions. Quaternions are applied to mechanics in three-dimensional space. They are also used in computer graphics to describe and compute mathematically rotation in 3D space. Here's a few citations for if you want to learn more, and here's a great video that shows how to visualize quaternions at work when you're mathematically figuring out how to rotate something in 3D space. Thank you for your time.